process, and we're going to actually design some things today and do some analysis. So I really enjoy this lecture. This is a cool one. I want to give a short shout out though to Rob Carnes, the super senior back in the corner, who's auditing the class. Rob's an old friend of mine and actually sponsored my PhD. It was sponsored through Battelle, the big defense researcher, when he was there. And I worked with Professor Hosoi during my PhD, and Rob and Pekko Hosoi and I put together this really fun project on digging into underwater soils using small, lightweight robotic systems. If you Google RoboClam, you'll find all kinds of stuff about it. But the technology was based off razor clams. But quite literally, I wouldn't be standing here today without Rob, because he basically took me under his wing and said, "I want to fund this guy." Right? And then he was just a real catalyst, like, you know, encouraging me, putting me up for awards, like all this good stuff over the last few years. So I owe him a lot. Thanks, Rob. And I just made him feel very uncomfortable. Give me a shout out. Okay, so let's get into this. A few announcements. Remember, we're doing the lab space intros tomorrow, and then you're going to do some more next week if you can't make it.
People said Tuesdays are good, so I'll probably try to do some on Tuesdays.
Okay. Please email Michael your team times when you're meeting and where, so we can come and check it out. And then anybody interested in driving some Tata Nanos? Yeah, like general interest, like even if you're not on the team. Yeah. We can like crank them around parking lots. All right. So they're not great at doing handbrake turns. Yeah, don't ask me how I know. They're a little top heavy. But yeah, they're pretty fun to whip around. Okay, let's jump into this. So, you know, just to give a recap on the last lecture, you know, we talked about the design process and going from like messy, you know, lots of little things, putting them together, ending up with a final thing. And so we looked at a few different ways this is taught in classes at MIT. So like in 009, what Slocum teaches in 275, going from course to fine, what's taught in 2744, this kind of top-down view, ask, observe, experience. And what I want you guys to be doing in this class is really combining that top-down and bottom-up view. Like while you're designing your stuff, remember what the user-centered perspective is and what they're thinking about, how they're going to use the device, how it's going to interact in their life at the end, but also break it down into small parts and take a big intractable problem and build it up into a final solution. So, you know, to recap, or not to recap, to summarize all this, the way I view our design process in this class is kind of a mixture of all these things. So it's very important at the beginning of your projects to nail down what your design requirements are. These are what do you want to accomplish, right? Then what you're going to do next is create strategies, right, for how you could accomplish that what. And you're going to want to create a lot of ideas. More ideas creates better ideas. And you're going to go through an evaluation process, and we're going to do one of these today, of picking out, you know, what would be the best idea. Then that how becomes the what for the next stage of the process, which is your concepts. Now, a strategy is kind of a high-level depiction of the approach you could take to a problem. And it's really good if you can articulate it without a physical embodiment. You know, think about it in terms of energy or speed or force. And then when you get to concepts, then you start thinking of actual physical systems that can accomplish these strategies. So you go through the same stage or same process, getting a bunch of concepts, figuring out how to pick the right one. Then when you get to your concept, you're going to have to break that up into small parts, right? This is like the bottom-up type approach. You break up this bigger problem into smaller problems. And when you guys develop your most critical module, that MCM is the most critical part of the project that if it goes wrong, it'll kill your whole idea. Right? It's really the linchpin of the whole design. So you guys will develop that, and you'll again come up with a bunch of ideas, and there'll probably be other more straightforward modules that you still have to develop, but they're not as critical. Then you'll take the best of all the modules, you'll put them together, and you'll come up with your final prototype or feasibility study or whatever your deliverable is in the class. So as far as the breakdown of the syllabus in the class, this is what we're going to be covering when I do the one-on-one design reviews with all of you in 2 weeks. Right? So you're in this stage now of doing background research, talking to your partners, figuring out the trajectory of your project, and figuring out what problem are you going to solve. Then we're going to do the concept presentations in class in lecture period, the MCM presentations in lecture period, and then the final presentation at the end of the semester on like December 12th, I think. So one thing to keep in mind when you're going through this process is that you're going to set a trajectory for your project right at the beginning of the semester. And if you define your design requirements poorly, it may lead you down a trajectory to just increasing badness, even though you might have a great idea. So, you know, an example of this that we saw a few lectures ago, I think, is the life straw. Great idea. You know, I think totally legit, really good idea, but they made some assumptions at the beginning and started marching down a course where they ended up with something that I think was pretty suboptimal. So instead, really try to set yourself on a good trajectory at the beginning of the class. And while you're going through this process, keep iterating, keep looking back and saying, did I make the right decisions? Question your assumptions, go back to talk to your partner, and don't be scared to, you know, iterate all the way back to the beginning. Like, this is what happens in design. You have to keep looking back and seeing, am I going in the right direction? Okay, so let's do an example of evaluating this should be an example, well, it's a concept and strategy. But are you guys familiar with this product, the Play Pump? Anybody not? Okay, luckily we have a quick video. So here's a quick video about the Play Pump.
Welcome to the channel. My name is Jay. Jay is your person, Mr. Sandra Hay, Director of the NGO Roundabout Motor Solutions. Thank you for coming to it.
Thank you
for joining us.
No, great. Lovely to be here.
So, tell us more about Roundabout Water Solutions. What does the NGO do?
Roundabout Water Solutions is an NGO which is trying to provide clean drinking water to rural communities, especially rural schools, where there's an existing borehole where we can put one of what we call our play pump.
Yeah.
And the play pump is a children's merry-go-round that we place over the borehole. Then as the children play on it, it'll pump up clean drinking water.
So what need then did arise for you to come up with the play pump inventions?
Well, one of my colleagues was actually out in a rural area and he saw these children walking long distances to collect water from rivers. And he thought, wow, you know, the power of children always wanting to play, these children be taken out of school, sent to collect water from rivers. What happens if we actually use that power of the children to bring up the water at their school?
Yeah.
He then met some farmer who had invented this play pump, and the idea was that put them into schools, so instead of the children going out of school, they've got something to play on, so that encourages them to go to school and love play on it, it's like that.
Yeah.
And at the same time, without them really realizing it, they're actually pumping water.
When you put the
All right,
play pump,
so that gives you an overview, right?
then what are the
So the idea is it's a water pump, and I think this sounds like a pretty good idea at first look. You've got children, they have boundless energy, they're running around anyway. Why don't we put some of that energy to good work? So the idea is, and she said this in the video, sorry for the horrible closed captioning, I hadn't actually read that until right now. I don't know, that's some bad voice recognition software or something from YouTube. But they said they're installing it where they have existing boreholes. The pump is on a merry-go-round, so kids play, it lifts the water up into a water tower, and then you can use the water and distribute the water. So the strategy here is that you have a human-powered water distribution system. See, you can say this without picturing the physical embodiment. The concept is that you're pumping the water with a merry-go-round with kids, right? That's the physical thing. So is this a good idea? What do you guys think? Yeah.
On paper, it was written that it's not very efficient, and you need like more children than necessary to actually pump it all the way.
So, yeah, but could we figure that out as engineers? Right? Like, I literally get grant proposals with stuff like this in it that I'll read sometimes, and I will do a quick calculation and be like, this is viable or this may not work. So let's think about it a little bit, right? So you have a water tower, right? And this has some volume associated with it. It's 10 meters off the ground, right? How much water might you want to distribute to a village every day? Or how big's a village? 100 and, I don't know, I'd say the median village size, at least in India, is 2,000 to 5,000. I'm just saying, okay, let's use multiples of 10 here, but it's order to 1,000 people, right? Do you guys know how much water people need per day?
4 to 6
About 3 liters, right? Yeah, that's good. 3 liters per person per day. And a typical water tower height is going to be about 10 meters. So what's critical here? What do we have to think about from an engineering perspective? Right? Yeah, I heard power, and there's the play pump here pumping. So you have power coming in here. Okay. And then what are you using that power to do? Lift the water. Okay. So how much energy would be in this system? How much energy do you have to impart from the play pump to the water power each day? MGH. Good stuff. Yeah. Which is the density of the water times the volume of the water times G times H, right? So this is 10. This is 3 per person. And then times 1,000 people, right? This is 10. This is 10. So you get 300,000. What are the units? Joules. Yeah, this is, I'll just write it out. It's 10 kilograms per meter cubed. Then, this is your volume right here. So it's 3 people times 3 times, 1,000 people times 3 liters per person. Cool. And then 10 meters per second squared times 10 meters high. And then we have to convert this into meters cubed. So there is 1,000 liters per 1,000 liters per meter cubed. Okay. And that is 300,000 joules. That is right. Thank you. Yes, it's 1 kg per liter. Good call. Good. That works out. All right. So what do you think? Could kids do this? Is 300 joules a lot? How do you figure that out? Okay, you could look at food intake, but how much mechanical power do you think a kid could put out? Well, we could look at how much mechanical power people can put out. So people have done a lot of tests on this over the years, and this is do you guys know the professor here, David Gordon Wilson? You ever heard of him? He wrote a really cool book called Bicycling Science, and it's all the physics and stuff on how bicycles work. And this is a plot in his book, and it's showing how much power you can put out versus duration, right? Like a power lifter in the Olympics can put out huge power, but it's for a split second. Whereas like a marathon runner is going to be a lower power for a longer amount of time. So we're talking about kids here. How much power do you think a kid can put out?
100 watts.
Well, let's see. And remember, they're playing, right? They're not being like whipped to like work really hard. They're playing. So a healthy, average man for 1 hour can do around 1 to 200 watts. But we're talking about little kids. What do you think they can do? 30 watts? Yeah, I guessed around, definitely less than 50. Sorry, I'm trying to unbutton my cuff. I guess around 50. An adult can do about 200 watts for an hour. I think a child's about 20, right? So, how long would a kid play on a merry-go-round? Not very long. What do you think? 20 minutes, half an hour? Yeah, 5 minutes. I guess about 10 minutes, right? So if you have E per child, that's going to be equal to 20 watts, which is joules per second, times 10 minutes. How many seconds are in a minute? 60, which I put on the wrong place. 60 seconds per minute. Okay. So we have, what is that, 200, what's 200 times 60? 12,000? Okay, 1,000 joules. So how many kids do we need to do this? No, it's not too bad, right? So we have 10 minutes to play, 20 and 25, right? If you do this, if you do 300 by 12,000 joules per child, right, you get an answer that you need about 25 children. What do you think? Is that feasible?
child doesn't play alone on the merry-go-round.
Yeah, they play with, that's why you need 25 children.
I mean, like, if there's 25 children, like, assuming that both, like, 4 children play together, they
Yeah.
would be playing, like one at a time for 10 minutes each.
They would each be contributing this amount of energy per play period, right? So there may be one child on there for 10 minutes and they do 12,000 joules. Then there may be 2 children on there for another 10 minutes and that'd be 24,000 joules, right? Or it could be 25 children on there for 10 minutes. But each kid, if they're playing for 10 minutes, would contribute this amount of energy into the system. That's what I'm saying. It's kind of independent on how many are on there at one time.
Then related with how much time they spend rotating.
They are. They're spending 10 minutes playing on it, rotating.
But then if there's like 8 kids sitting on it and one kid is rotating,
They're still putting in this amount of power. Yeah, it's a good point. So you can have more kids on it. That merry-go-round's going to have more mass, right? You will have more kinetic energy in the system. But say that kinetic energy gets dissipated by pumping water, they're still putting this much energy into the system. Okay? Yeah.
Well, you also have to look at the mechanism, right? I mean,
Ooh, yeah.
12,000 joules per K.
Yeah.
That's considering whatever chart you showed us, but the merry-go-round has a certain, I guess, ability to convert those 12,000 joules into some sort of energy.
So there's efficiencies, right? Yeah. What else?
So this is like assuming if like the merry-go-round stops spinning right afterwards, so if you want to continue like the child was playing, so the energy would need to like continue.
Yeah, it's a good point.
Like fun.
So if you're just putting in that 20 joules or 20 watts just to pump water, it would be a merry-go stop, right? Just push, 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 stop, right? So you want some kinetic energy left in the system so it keeps spinning. It's a good point. That's what makes merry-go-rounds fun. You had a question, Rob?
I'm just going back to the point. You figured out how many liters per day.
Yeah.
For a voltage fast.
Yeah.
But that assumption is not continuous throughout the day. So how does the merry-go-round match with the assumption for water?
That's why you have a buffer tank.
Right, exactly. So
Yeah.
where I'm going to is the other design factor is having large enough buffer.
Yep.
Requiring capacity to make
And so this volume would be 3,000 liters at least. It's probably going to be more.
it be more than
Yeah. Right?
Yeah,
do you think?
So you do the power balance to pump water from the ground to the tower, but where's the water table? Like,
Ooh, good point. Right? The water table's not even shown at the surface here. Water tables at the surface are better known as lakes or ponds, right? This is a bore well. She said it in the video. So you're picking up on a good point. Like, is our height that we're lifting actually 10 meters? So let's dig into this a little bit. First, let's think about what it's like for a child to put out 20 watts. I think they can do it, but how would it feel? I think it would feel kind of like man-hauling, right? Do you know what this is? Have you guys ever seen a picture of this? This is what like Antarctic explorers did at the turn of the century to try to go discover the South Pole. And you probably, what's the name of the guy who froze to death? Or he ran out of energy?
No,
It's not Shackleton.
one of them, but they literally got negative energy.
Yeah, these guys, Google this, I can't remember their names, but there was a group of British explorers that were doing this man-hauling, and they literally couldn't eat enough every day. So they got to the pole, but they couldn't get back because they couldn't haul enough food, and they ended up freezing to death and dying, and they were discovered relatively recently. Whereas there was a group of Norwegians also racing the pole who took sled dogs and just zip there and zip back, and they were like, done. So 20 watts is equivalent to carrying a 20 kilogram load, so 44 pounds, up a 10% grade, pretty steep slope, at 2 miles an hour, walking speed. That's man-hauling for a kid. Imagine like your little like Western Flyer wagon, like dragging up a couple dumbbell plates up a 10% grade. That is not very much fun. Kids could do it, but it sucks. The next is, yeah, you pointed out, merry-go-rounds are fun because you put kinetic energy into the system. Not all the energy can go to pumping, or else, as I said, it'd be a merry-go stop. So what happens then if we put half of our energy in for kinetic energy, half for pumping, as we're riding this thing? You need 50 kids. Yeah, exactly. So you need 50 children. But then somebody brought up the point of lifting from a borehole, right? So if we have a 10-meter deep borehole, how much more energy do we need? Double, right? It's 2 times more energy. Now we need 100 kids. And then you brought up the point about the inefficiencies, right? So just a ballpark, let's say it's 50% efficient. Now we need 200 kids. And remember, this is a 1,000-person village. And then also remember that some days it sucks to ride a merry-go-round, right? Like if it's hot or if it's rainy. Is this a viable source of delivering water? Like, no way. Not at all. And this is the type of calculation that I want you guys to do. And this takes, just 5 minutes to crank through this and be like, ooh, wow, this doesn't look too viable. And that's the type of stuff that we can do, as engineers. And it's like thinking about the kind of the socioeconomic situation, like how many kids are there, how long would they play, blah, 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 and then putting some numbers to it, right? This project has received millions of dollars in grant funding over the years. It's been, it was kind of held up as like this success for a while, and then people, I think somebody here said it, like people have debunked it, and they're like, no, this doesn't really work. But it still exists. The website's still active, and it's a compelling story. It's like, yeah, boundless energy, kids can pump water, but it's not viable as a solution. So you guys need to think about that. Okay, let's talk about what you read over the last week. IDEO's Human-Centered Design Toolkit. Yeah.
So, reading the book that actually made me think about the play pump.
Sure.
Because the two of the harshest criticisms I've heard is that one, the play pump ended up being like manual labor for children.
Yeah.
The way they could get enough water. And they actually replaced the old pump with the play pump, so it was the only way to get water. So like people are getting motion sickness because they couldn't just pump with a normal vertical pump.
And I've heard you see like moms out there like slogging around the merry-go-round to pump enough water up out of the ground.
Yeah, so I've been using this toolkit where it's like there was a big error.
Huge error. Huge mismatch in like the performance you need and what could be delivered from that power source of kids. Okay, so what do people think about this? What were the 3 main messages here? It's kind of 3 main words that you hear throughout this thing. Yeah.
So, I'm not sure if you're referring to this, but I think it was hear, create, and deliver.
Deliver. Excellent. Good work. Okay. So what do you guys think about this process? What do you think about their approach? Yeah, Jimmy.
I thought their research aspects were really cool, how they separated qualitative and quantitative research.
Mm-hmm.
Qualitative was like really good for getting at concepts, but then you needed to kind of add enough quantitative data kind of towards the end of your design process. Because I think we normally think of research like we're like,
We think of research as what?
like at the beginning of the process. Right?
Yeah.
We're like research is starting and like do it.
Yeah. They have this picture in the book, right? And I like this picture. It's another like design process. And you see don't look at that yet. You see these initial observations, and then it looks like there's kind of more work here happening in the create phase than you deliver. But what do you guys think about this process and this depiction of actually delivering a solution? Yeah.
It works when you're going for this type of designing initiative, like when you really need to like hear what people want first.
Yeah.
But that's not always the way designing works. So it's like it has a limited effect, but when it is needed, then it's like very useful.
Yeah. There's also one line here. Right? That's something that catches me. Yeah, what do you think?
I was just going to say that they spent the same amount of time in the hearing part as the delivery part. And the harmonies engineers tend to think that you gotta focus your energies in actual making, but you realize that you also have to spend.
Yeah.
I'm just curious, what's the vertical axis again? Is it amount of work that has to be done?
I don't know. They don't put a vertical axis. What is it? It's what?
Abstract on top of concrete.
Oh, abstract and concrete. Okay. I had forgotten. Okay. Well, do you guys know? Yeah, go ahead.
It's also the hearing part shouldn't necessarily be its own distinct section. You should be getting feedback as you're working on it, as you're creating it. And you shouldn't just stop taking input once you started, the concepting part of your work.
Mm-hmm. What else?
Just to add on to that, it's also like implementation plan done. So I think we talked about also in the beginning of the class that like you should get feedback from people and then do like maybe a version 2 and just keep innovating based on what you're doing, not just be like, okay, I'm done.
Yeah, you may not just be able to wipe your hands of it. So let's say, okay, look at where prototypes is, and look at this amount of like time compared to this amount of time. Can you go to market that fast with a prototype? I don't know. Better designer than I am, if you can. Yeah. This is a great point. Yep. No, I was hoping you pick up on this. You expand on that.
So what IDEO does is they do like the very early stage research to early stage prototype, and then they hand it off to someone else. So they expect this to work for their model, and it works for them. Most people don't just hand off the earliest stage prototype.
Yeah. Yep. Yeah. So if you're not familiar, IDEO is a product design consultancy. And what happens typically is a company will come to them with a need, you know, of creating a new product or creating a new idea or service or user experience. And IDEO will put a lot of time into this creation period. This is their bread and butter. This is what they're excellent at doing. And then they typically hand off that proof of concept or pre-production prototype back to the sponsor, and they take it to market. IDEO doesn't make products. And I think this method reflects IDEO's engagement with consumers and IDEO's engagement with clients, you know, that they're not a company that takes it to market. So a couple things that stood out to me is when you're hearing from whom, like they talk about in the book, like going to a village, right, and talking to people, but is that the only group you might want to hear from? You know? I think they got a lot of this like really right, and they did well. And end users are really important. But who else could affect, like if a product's brought to market? Yeah. Like we work, you know, we've done a lot of work with Tata Chemicals on a water purifier, and they would tend to break when they were being delivered from the factory out to rural kiosks because the roads were bumpy, right? You got to think about like weird things like delivery issues and road quality. Somebody else has a question? Yeah. Yeah. There's a lot more to think about. Also, this can take months, right? And I'm gonna, you guys read about our decel project. That took 2 years to do this. We actually spent more time on that than what we've spent since then, right? And there can be a lot of iteration back and forth here to nail down these requirements and understand. Okay, then in the create phase, how would you guys manage your own biases? Right? If you're working for IDEO out in San Francisco, you know, and you go over to Kenya, you've never been to Kenya, right? And you may have a conception of what life should be there, but maybe it's like your life, but maybe that doesn't match. Like, how do you manage that? Yeah.
I think it's having a fairly diverse team to begin with. You're not going to be so great at kind of self-monitoring your own biases, but if you have enough opinions in the room, you can flush out the best ones.
Yeah. Yeah.
I think that's like another reason why the hearing and creation phase are pretty key to be like pretty intricately linked. Like it's pretty important to think of the end users as part of your team in some circumstances.
Yeah. I think that's important too. Yeah, what do you think?
I think also another strategy for that is to be always aware of the social politics of the situation. When you go to these encounters, trying to get feedback from people, especially when you work in like what they focus on in this toolkit, working with emerging developing markets, coming from as part of an NGO, as someone coming in trying to drive engineering for development, you're always gonna be an outsider to the community, and you always keep it in mind because the conversations you have with your constituents is very different from what they would have with each other. So.
Yeah, I think that's exactly right.
Maybe a good way. I think this is one of the fundamental things in ethnography and anthropology. There's no real way to extricate yourself from that barrier, but you just always need to be aware of that.
Yeah, and you're going to read more about this in Hidden in Plain Sight, which is the next reading assignment. I think one of the most valuable things you guys can do is recognize what you don't know. Like try to like really identify it and like even list it out if you want to. Like I am not from this background, I've never had a prosthetic leg, you know, if that's the example. Like really like try to identify where's your value added, what are you bringing to the problem, and where are the big gaps in knowledge. You know, I think it happens too much that people here conceive of solutions for over there without any perspective. Yeah.
So I was going to say the book also talks about letting the customer co-design with you.
Sure,
So
I think that's great.
and have
Yep.
them design some aspects of the product.
And I'm not saying this is bad. I think this is a great resource for us, but I think in this class we can build on it, right? That's why we should reflect on this. How about like cultural differences in building rapport with people who are from a different cultural background?
So I think one thing that, so I had done some pro bono consulting for companies in developing nations, and one thing that really struck me in the writing is when we would go over there, we would always wear our like nonprofit shirts and like dress differently, and the purpose wasn't to set ourselves apart.
Yeah.
It was because somebody would want pictures and they could like advertise it later. And they talk through it here how that's not how you want to approach it.
Yeah.
And reflecting on those experiences, I can think of times where I think that kind of set us apart from the companies we were working with and the people we were working with. The other thing they talked about a lot was how you want to get people individually apart from the group because they're often more open to discuss things.
Yeah.
And I think that was really telling. That's something that some of the people I worked did a lot, and they got really good insights. But
Yeah.
I think that those two things in particular in the reading were really valuable.
Yep, I think that's great. Yeah, we oftentimes have to say directly to people, you know, like we're a team here. You know, we really value you being here, and we really value your knowledge because you have more, like as valuable or more valuable knowledge about the problem than we do. You know, if it's sitting down with like an amputee or a wheelchair user or something. And I think that like that helps to equal the playing field. You're not designing for them, you're designing with them. And then also I've been in situations a lot where I've had to really be upfront and say, tell us the worst things possible about our design. You know, really give it to us straight, because in a lot of cultures, like I really felt this in East Africa, people are so trained to be polite. You can give them the worst thing and they'll be like, oh, thanks, this is great, so generous of you. You know, and that makes you feel all warm and fuzzy, but it doesn't give you any good design feedback, right? Where does analysis come in here, into this process? Like we're engineers, where does this stuff come in? You know, that's so important. You guys have had, you know, 4 to 8 years probably of analytical training. Like use that, that's a huge tool in this space. What about business models? What about economic drivers? You know, figuring out if the product and the solution is economically sustainable. That's so important. And then like design for manufacturing distribution. I don't think these are touched on enough, and I think these are really, really important in this space. And finally, in the deliverer space, you know, I alluded to this earlier, you go from prototypes to product. Oh my God, this can be 10 times the time scale of the rest of this. That can be massively challenging. And I think it's powerful if you can think about that back at the beginning, you know, and think about those design for manufacturing steps and stuff. That'll get you to productization faster. You know, try to engage all of those stakeholders that are going to like, you know, either make or break your idea and help you get it to market. So you're going to read a paper next. This is due the next class, called Customer Value Chain Analysis. And I think the author's Krista Donaldson. She went on to start the company DREV, if you guys have ever heard of that. They're based in San Francisco. But I think this is a really, really good paper talking about this network of stakeholders that you have to engage and satisfy to bring a product to market. And there's like, you know, I love this, the corrupt government official. There might have to be money going to that, you know, to get the solution out there. I don't like it that it's an NGO example. Like I like free market solutions because they naturally scale and sustain themselves if people are making a profit. Like if you're doing a charitable solution, there's a limit to how much money you can put into that. But I like this graphic because you can see all these links in the chain of taking an idea from inception all the way to market, right? And if you break any of those links, it might kill the whole project. So if you can start a design process before you design anything by thinking about who are all these folks, and can you go and engage them and talk to them before you design anything, you're going to figure out constraints and requirements you wouldn't have realized otherwise. And you can start satisfying them from the get-go, instead of working for 10 years and then being like, oh man, it looks weird or it smells weird, people aren't going to buy it. I think this is actually an issue with academia a lot of times, because the model here is often like you come up with an idea, you get money for it, you develop it for a number of years, and then only after that ask, could we bring it to market? You know? And like, if you didn't realize 5 years ago that it's just inherently going to be too expensive or some other reason that it'll fail, it might not go anywhere. You know, you guys can prevent that by mapping this out from the beginning of a project. It's so important that you engage subject matter experts in this design process. And the reason we work with all these companies in this class, and instead of you guys just creating projects on your own, is that they have so much knowledge about the markets that you're designing with, you know, designing for. And so, you know, you want to be interacting with, like, you know, you're going to be interacting with like the engineers and stuff at the company. They're going to be interacting with the marketing folks and the farmers that are, you know, the marketing folks that are going out to the fields and meeting with the farmers. But you need to be collecting this information from this whole group of subject matter experts. And what's challenging about this class is you can't go there yourself oftentimes, but I want you to realize that there's a lot of other players that you need to get feedback from, but you may not be able to connect with directly. And your partners can help you connect there and get information from those folks. You know, so again, this is why we work with organizations like this, Jane Tata, Mahindra, International Development Enterprises was one of our partners in the past. And what's good about these folks is that they know about the markets we're trying to work in. And in all of the cases you're working in, they've been working there for a number of years, right? So they really have a lot of insight. They can manufacture and distribute solutions, particularly the companies, and I think that's powerful because they're going to be able to give you feedback on those factors, like those additional factors of design that may not be apparent to an end user or to you guys in the design process. And then particularly with the companies, like, you know, these three are companies, they have an inherent economic viability, hopefully, in the products you're helping them design, because they're trying to sell for a profit, right? If they can make it and distribute it and scale it, they're going to make more money and they're going to make more products, and, you know, you can impact more people or make more money or whatever the objective is. So when you're engaging your partners, you know, some of the things to consider is, like, this is really important when you're starting to scope a new project, is like really trying to understand what is their objective. What is the objective behind the projects that you're doing? Are they trying to benefit people's lives? Are they trying to take over a bigger market share from a competitor? Are they trying to engage a market that doesn't even exist yet, right? They see these potential consumers, but they're not there yet. And in all of your projects, you are addressing some sort of technological keystone behind the project. All the companies or partners have come up against a hurdle that they don't know how to get over, you know, the keystone of the problem, and that's the rigorous engineering we're bringing to the table. And like, this perspective is what I think about a lot when we're defining projects for my research group, right? Like MIT doesn't make or ship products. You know, I don't live in a developing country, but we're good at math and science, right? And the projects we tend to take on are ones that have a really hard technological keystone. And once we figure that keystone out, the partners are in a position to commercialize it, right? And you guys are in that exact same position in this class. You're figuring out keystones. Big thing here is to listen to these folks, right? And hear what they have to say, ask a lot of questions, and don't be afraid to push back on assumptions. That is an uncomfortable thing. Has anybody experienced that yet? Have you talked to your partners? Yeah, you have already in the class? Just this morning, what happened?
So yeah, I mean, they started off talking about like what they wanted out of the project.
Yeah.
I guess we were going into thinking like looking for energy efficiency for the cooler.
Yeah.
And I mean, not really an assumption, but their underlying goal is profit, essentially, like to reach out to smaller consumers, to smaller retailers, and get it as far as possible.
Yeah.
So like energy efficiency isn't a big concern for them, so they're essentially hoping we can get an energy efficient, cheap product.
Yeah, the energy efficiency is affecting the cost, right? And they're worried about the cost. That's really good. Yeah. That's like, I don't know, like you find these mismatches all the time, I think, I see it in health technologies a lot. Like, people in the US will be like, oh, these poor people don't have whatever clean water, and they're like, we have to change their lives from our perspective, but the perspective there might be very different. And it's great you picked up on that, And you should, if you think they're in error anywhere, you should push back. Okay. The next thing I want you guys to consider is that when you're working with your partners, there might be a whole hierarchy of stakeholders within one organization, right? And I like this example from our drip irrigation work. We work with Jane Irrigation on drip irrigation because a few years ago, I started talking with Jane about their company and what their objectives were to increase the impact of their company and increase the growth. So, talking to the executives of the company, they want to expand drip irrigation. That's their bread and butter business. They want more consumers. They want to make more money. And I had to work down this hierarchy within the organization to understand all the facets around what would it take to expand drip. So I had to talk to the division heads and the engineers and understand what makes drip irrigation hard to expand in the market? What drives the price? What drives the plant growth performance? Where are there areas for improvement in the technology? I had to talk to the production engineers and understand what's expensive in the drippers, which is silicone. They use silicone in part of the dripper, but the plastic they use in the injection molding, that's cheap. That could be a design freedom you could leverage, right? And then the user and distribution factors, like what are the relevant price points, how would people use this, how does it fail? And we put all this together, and we found that if we could cut the pressure required for these drippers, right now they run at 1 bar of pressure. If we could cut their minimum pressure down to 0.1 bar, it would drastically reduce the cost of these systems. And we have to make drippers that they're called pressure compensated, which means they can do a constant flow rate, a variation of pressure. They had to be cheap, we define a price point, and they couldn't clog easily. So these are the core design requirements that we articulated. But what was crazy that came out of this is that as we continued talking, we were considering the whole system behind the drippers. So you have a series of pipes that connect to these little drippers and deliver the water to them. And Jane makes 2 styles of pipes. A hard pipe that doesn't flex easily and has more plastic in it than a flexible drip tape pipe, which is it can collapse down flat, easier roll up into a roll, and it has less material in it per length. And so we obviously wanted to go with the cheaper pipe. And we were talking to them about that. We wanted to go to the cheaper pipe with less material. And we were talking to the executives. Oh, sorry. We had to do solar power. But anyway, we were talking to the executives, and they came back to us and said, no, you have to use a thick-walled pipe because that's the only one the government subsidizes. And so it's actually cheaper to the farmer to use the more expensive thick-walled pipe than the thin-walled pipe. And I was like, what? That's totally counterintuitive, but we only understood that because we talked to the people who know Indian government subsidies. That's a really complicated network to navigate, and we're not as knowledgeable about it as these guys are. And what was interesting about this example too is that at the end user level, farmers don't like the thin-walled pipe because when a bullock, like an oxen, steps on it, it punctures. But the thick-walled pipe doesn't puncture. So the users prefer it. And I love this example because this requirement came from the top in the bottom of this hierarchy of stakeholders in one organization, right? And they impose the same constraint. And we only got to it by listening, right? But again, don't be afraid to push back on assumptions. We have to do this all the time. And Jane's a great example. One thing we run into all the time is they'll say, oh, we can't buy a pump to do such and such performance. And I'll be like, well, that's different than the theory not existing for how to design a pump. Maybe we do have to design a bit different pump, but it looks like it's physically possible. Just because you can't buy it off the shelf doesn't mean we can't do it. And that type of engagement is really good. Okay, so let's go through this example of defining design requirements, which you guys read over the last few days on our work on desalination in India. So this project started actually with Jane Irrigation about 4 years ago now. And Jane's a big company that deals with water. and they said, you know, most of our users are poor rural farmers. They don't have clean water. We're a water company. You do irrigation, so we should be able to do something about this. What do? And this was a crucial starting point, because we could have jumped in and said, you know what, we're going to make a water filter that'll get all the bacteria out of the water. Or we're going to make a reverse osmosis system that'll get all the salt out of the water, because we've seen that done other places. You know, let's go forward with it. We didn't do any of that. We instead took a step back and tried to ask, like, what is the environment telling us that the best solution should be in this context of India? And so we started digging into this, like the socioeconomic side of this. And the big thing that stood out is that if you look throughout the country, 60% of the groundwater of India has salty enough groundwater that you can actually taste the salt. You can drink it out of the ground and it would taste salty. So anywhere where you see a color other than blue here, the water would actually taste salty as you get it out of the ground. So salt is actually the most prevalent contaminant in the country. Then what further makes this challenge really difficult is that the groundwater you have available is already really water stressed. There's not a lot available. Like, farmers literally can only grow like 1 or 2 out of the 3 seasons of the year, because they just run out of water in the ground. It's not getting replenished enough. So because of this raw water stress, we had to think about how can we best utilize the water we have available. Now, not all is bad here, because where you have really salty water and where you have a lot of water stress, you actually also have a lot of solar power. And this is a map of solar radiance versus the land area of India. So, you know, over here you get a lot of sun power. And this is important because the majority of the small villages throughout India, even if it says on paper they have grid access, what that technically means is that one household in the village is connected to the grid. And that grid only may be on for 2 hours a day, right? So the majority of these villages actually don't have reliable grid access. So solar power could be viable here. What we did is we put together this information and started making kind of a detective case of what would be the most viable solution in this space. So, you know, because of the prevalence of groundwater, because people don't like drinking it, and because, so like in the next 10 years or so, India's consumption rate of fresh water is going to exceed its replenishment rate. It's like really in dire straits as far as water stress. So all this pointed us to the fact that we had to desalinate the water if we were going to make clean water for a lot of people, and we needed high recovery. And what this is a measure of the product water you produce relative to the input water to the system. So this would be 10% wastage, 90% recovery to product water. We want to maximize the water we have available. Then we had to contrast this with like the technical side of the problem. So as I said, villages typically don't have reliable grid access, and we had to do some more digging to figure out what sort of villages would we want to engage. It turns out that the median village size in India is 2,000 to 5,000 people. This accounts for 1/4 of the country's population, and so those people would need 6 to 15 cubic meters of drinking water per day, right? So that's 3 liters per person per day in those villages of 2,000 to 5,000 people. And given the limited access to grid power, this pointed us to photovoltaics as what looked like a viable water source. So then we had to figure out what technology seemed the most appropriate in this space. The industry standard is reverse osmosis, right? And if you guys remember from high school chemistry class, if you have 2 salinities of water, the water at the low salinity will kind of get sucked over into the higher salinity side to try to balance out the concentrations of salt, and you'll end up getting this like actual head difference of the water on each side due to this osmotic pressure. What reverse osmosis is driving that process backwards, so you contain the salt on this side and you produce your low salinity water on that side. So that was our main candidate. But we did a lot of digging on different technologies, and the other one that looked potentially viable was electrodialysis. So this is a technology that's used mostly in industry, like big industry, for like juice making and like concentrating like sugary, like electrolyte substances. So the way it works is you have an electric potential, so voltage applied over an anode and cathode. You have ion exchange membranes, which can either pass a positive or negative ion, but they'll block the ion of the other charge. And what you do is you feed the saline water between the membranes, the ions get pulled towards the anode or cathode, and they can at most only travel through one membrane before they hit the next one. So what you end up with is an alternating channel of diluate, which is your desalinated water, and your concentrate, which is your saltier water. So the big insight that we had was that when we looked at the salinity ranges you find in India, which are much lower than seawater. Seawater is around 35,000 parts per million, whereas groundwater in India is around 1 to 2,000 usually. Electrodialysis requires only about half the energy compared to reverse osmosis for that salinity range. Why that is a potential game changer is that currently PV-RO systems have been tried, but they're not economically viable because more than 50% of the capital cost of that system is in the photovoltaic power system, right? That blows the budget. But we can cut that cost in half, that power system cost in half, and we're seeing that it looks like we're going to be able to make off-grid electrodialysis systems that are as cheap or cheaper than on-grid reverse osmosis systems, even including the power system cost. So this was the really big insight that came out of doing the technical detective work, like really going into the energetics and thermodynamics of the problem. So, we put this all together, and from an energetic and cost benefit, and this pointed us to photovoltaic electrodialysis. And I'm giving you this story, and this is like much deeper than I expect you guys to do in the class, but it's the same type of theme, right? We had to dig into the socioeconomics on this side, and we had to dig into the technical part, and it gave us a really disruptive insight. And then we've generated a huge amount of funding around this in the last few years. And actually, we won the USA D-Cell Prize last year. This is our first full-scale, village-scale system, about 10 cubic meters per day production. We've done another pilot this year in India, and we're doing another one in Gaza in another place in India this year. So we got a massive disruptive insight out of that detective work, and we're only now starting to read about other groups around the world who are saying like, hey, we could use electrodialysis to desalinate water off-grid. Like, we got a 2-year head start on those folks by doing this detective work. And then, big funding agencies are really stoked about this and funding us to continue developing it. So I want you guys to always be digging into that technical and socioeconomic factors. Okay, so just to sum up, like defining your design requirements and strategies, you need to understand where the motivation of the problem's coming from. What is your partner going after? New markets, more revenue, etc. And why should you go about solving this problem? Why is it a meritorious problem, for us to solve? The second is understand this whole network and chain of stakeholders that you would have to satisfy to bring a solution to fruition. Right? What do they need? How does that dictate design requirements in your project? The next is you need to think from a user-centered perspective, try to learn about their lives. And this is hard for you guys because you're here. But talk to the marketing folks at the companies you're working with, right? Try to understand like how their marketing folks has empathized with them, why people would buy the products, what is the value proposition the company's making. The Pepsi one is a really good example. People like cold drinks. How much do they like it? How long would they be willing to wait for one? That's a big question for you guys. Say you can push that 15-second rec to 30 seconds, then you cut your power in half. Think from a machine design perspective, right? What are the critical physical or theoretical relationships, in this example, that you can work out, in invalidate solutions or see that solutions have more promise. You guys have the tools to do all that, and we're going to be pushing you to do that in your projects as you go through this class. Right? From an engineering perspective, what would constitute a successful solution? And then finally, I want you to design requirements or define requirements as quantitatively as possible. This is a mistake I see a lot of our grad students make, in the qualifying exams and stuff, where they say something has to be low cost or lightweight or low noise. Put numbers to that, right? Dig deeply to see how much could this cooler cost? What is the value to the consumer? How does that affect the price point of that Pepsi cooler? Instead of saying quiet, if you're on the Tata Nano vibration team, get a decibel spec, from Tata Motors. They probably know it. Okay, now we're going to do another example, right? And this is one, whoa, I should plug my computer in. Forgot to charge it. This is one that you're probably familiar with in the developing world technology space, in-home lighting. It's great if people can actually see after dark because you can do things like study or interact with people, good stuff. So I'm giving you the requirements that this thing is going to be off the grid, so it has to use renewable energy. It has to light one room of a small house. So let's say a 10 by 10 foot room, right? You have to keep that light on 4 hours per day. You have to be able to recharge it in one day. And what are the ramifications about cost and size and installation? What are these other factors we should consider? So starting out, what do you think the light source might be in this house? Like, what do you think will actually emit the light?
LED.
Yeah, you could use an LED or incandescent bulbs or, you know, bacteria. That's not a bad idea. Maybe. Why not? Bioluminescent bacteria?
Use a skylight.
Not at night.
Yeah, so it's 4 hours.
4 hours at night. Yeah, 4 hours at night. Yeah.
Use the electrofluorescent tape that they use in exit signs.
Yeah, they could use that. You could use fluorescent bulbs. So like one bit of research that I would do in this is start getting a frame of reference of how much power do these light sources need. I don't have bioluminescent on here, sorry. But you know, you can, I did this in a really quick search and it shows like the different types of lighting solutions and how much wattage they need. So like I grew up with incandescent bulbs, so it's easy for me to think in like incandescent wattage, right? Like 100 watt, I think around 100 watt bulb would light a 10 by 10 room, right? Would you agree with that? Yeah, I think so. So you can see like how much power you would need for these different solutions. So what would lend itself to this problem, do you think? You know, what would be a good solution maybe as a light source for off-grid? Yeah, LEDs. I totally agree. You know, that's a little bit of research you got to do, but I like the bioluminescent idea. I think that's cool. So let's just put that over here. Let's say we need the power going into the light is approximately like on the order of 10 watts. Okay. So now, what are the strategies for the power source here? How could you power this light system? Let's work out the energy too. Right? How much energy do you need? If it's that LED system, how do you work that out?
4 hours.
Yeah, so you got 10 joules per second times the time, 4 hours. And then how many seconds are in an hour? 3,600 seconds. Okay. How many joules is that? Somebody calculate that. 40 times, it's like 160,000-ish? 140,000-ish? Do you guys have iPhones? 144,000 joules.
Only like 100 children.
Yeah, there you go. Well, there's a strategy. So I'm asking you to generate strategies for this, right? I don't want you to think of devices yet, right? What are different sources of energy? Yeah, children's one. You can say, I can capture energy from children, right? So P, as we already know, P-child is equal to 20 watts. No, this is a really good strategy calculation, right? And how long could they play? You think 10 minutes? Yeah, so what was that? How many? It's up here. It's 12,000 joules. Man, so that equals, okay, 12,000 joules. So you need 12 kids, right? Yeah. So, okay, you need a big family. This goes back to family planning to light your house. Okay, 12 kids. All right, what's another idea? How else can you get energy? Solar, okay, I like that. So we have, here's child. Let's try solar. All right, how much power do you get from the sun? Depends where you are. Yep. Do you guys know, like if you take the cross section of the Earth and the sun energy hitting it, what it is? It's basically the peak at the equator. It's around 1,300 watts per meter squared. So, you know, the irradiance that's hitting the Earth, so P sun, and we're gonna have to lower this for a number of factors, is equal to around 1,000 watts per meter squared. Okay, but remember, that power over time is going to look like a bell curve, right? So if you take like an average here, What do you think it is?
7.
Yeah, I'd cut it in half probably, or less. And it's not over the whole day either. So let's say like 1/2 because of the, the bell curve. Who's that? And then how many hours a day do you think you're getting that half? I'd say like 5 or 6. Yeah? Yeah, okay, so 6 hours. And then we have to do 3,600 seconds per hour. What's this work out to be? Come on, geeks.
10850.
What is it?
10850.
10850. What are the units here?
50.
Oh, 108 and 5 zeros. Okay. Okay, like that. 10,800,000. Okay. What are the units on this? Joules per meter squared, exactly. So how many meters of solar panels do we need to generate this much energy?
Depends on the efficiency, right?
Yeah. Yeah, so let's calculate that. So we have 144,000 joules we need to generate. Yeah, and there's like conversions and stuff. In this, yeah, we haven't accounted the efficiency of the solar panel here. This is just energy hitting the solar panel, right? Hitting panel. Okay, so let's account for all those efficiencies. So we have 144,000 joules, and then we're hitting the panels with, I hate writing all these zeros, joules per meter squared. Okay, then what are our efficiencies, you think? 30%? Yeah, it's like around 10. Yeah, 12 is pretty good. Let's just say, because to work with zeros is 10% efficient, right? So times 0.1, this is panel efficiency. How efficient do you think your conversion efficiencies are? Because you're going into a battery and then you're going into the LED. What? 90, yeah. It's probably going to be, it's probably going to be pretty good, right? So, yeah, you could say 0.9. And this is the efficiency of the system. All right, so if we calculate that, what does it give us in units? Meters squared.
Wait, wouldn't you want to multiply that then instead of times it by 0.1?
Oh yeah, you're right.
Yeah, because it would be on the bottom and you don't need.
Oh yeah. Good point. So it'd be, good catch, thank you. Yep. So what does this work out to be? 0.15. Does that sound reasonable? That's meter squared. Right, you can think of a square meter, about a little over a tenth of it. Not bad, right? It's approximately this big, right? I don't know, it's going to be around that, but like, yeah, 0.15 meters squared. Maybe a little smaller. Well, how much would that cost? $100. You have, a refined palate for solar panels apparently. Like, no, they're much cheaper than that. They're about $1 per watt. Solar panels right now, right? So, if we figure out the cost of solar, I can't do it from that. I have to go back here. So we have 1,000 watts, or we have $1 per watt, right? And then we have this energy over that time. So we have 10. Yeah, we want watts in the numerator. Joules over, it'd be 5 hours, or 6 hours. right? Because you need watts to cancel out with watts. And we have a watt over joule per second. And then we have, we need to put in seconds here. So it's 1 hour, 3,600 seconds. And then we have to put in the efficiencies, right? So we'd cut down this by 10 times. So we do 0.1. That's your panel efficiency. So what's that equal to?
Would the efficiency actually be $1 per watt?
That's watt of rated panel power. So it does count for the efficiency. That's like the power you're getting out of the panel.
So I don't think that the
It says $300. Oh wait, divided by 6.
You've already read them for it.
Did I mess it up?
No, I mean,
No,
if
this
your
is
solar
$50.
panel puts out 100 watts,
Yep.
that's after efficiency, so that means that the efficiency doesn't enter into the calculation.
No, but this is the energy hitting the panel. So the energy hitting the panel times the efficiency is the energy you're getting out. I'm sorry?
That per meter squared or whatever, I know
Yep. No, this should have dollars as, right?
No, the per million quantity is joules per meter squared, so you need an area.
Good. Nice. Yep, so then you do 0.15 meters. What's that work out to be? Squared. 7.5 bucks? Sweet. Right? That's not bad. That looks kind of viable. Right? Yeah, but well, we cut it down, right? Like we cut this in half. We have the half there, right? So this is an estimate. I would expect you guys to do a bit more rigor here, but it gives you the sense. And we're doing this on the fly. That's like when I'm screwing it up. I don't have notes in front of me. But you can do these quick back of the envelope calculations to give you a lot of insight. This doesn't look bad, right? That's not crazy expensive. This is not crazy big, you know? Let's think of another idea.
Glow sticks.
Peltier effect.
Peltier effect. Huh, that's a cool idea. So you'd what, put something on your fire?
I was thinking it would be hotter outside of the house than inside because it's sunny outside, presumably, during the day, and then you could store the energy in a battery.
Okay. So you have, I think, you know, the power you're going to get is relative to that delta T. So you have a really small delta T. Where I've seen Peltier systems used is like when you have a fire, like 1,000 degrees, you know, relative to the outside.
I saw a flashlight where it was like your hand versus the interior.
Oh, really?
The hollow flashlight.
That's cool. Well, let's think of some other ways. Like, what if you dropped a weight, like a cuckoo clock, right? So let's think you have your black box that's outputting your light, and you're dropping this weight. Let's say you drop 1 kilogram, right? Because a person can lift that. It's 2.2 pounds. What's a reasonable distance you could drop it?
1 meter.
Yeah, let's say 1 meter. And we need, I wish I could put this one in the back, but we need 10 watts of power, right? So our power is going to be equal to 10 watts. How fast is this thing going to drop?
We'll have MVH power.
It's force times velocity, right? Which is mg times velocity. So m is 1 kilogram. 1 times 10 meters per second squared, kilogram. So our velocity is 1 meter per second. That would suck to do homework with, right? It's like you put it up, you like write something down, it drops in 1 second, and you have to put it up again. So you could increase mass, let's say 10 kilograms, then it would drop over 10 seconds. Well, look at the scaling here, right? To have, like, what would you need for an hour? You need 60 kilograms, 120 pounds-ish. I don't know, can you guys lift that? 1 meter? I guess. You could, but you're going to spend a good amount of time cranking it.
I mean, maybe you don't have to lift it. You walk up to a place and sit on a chair, which kind of lowers, so you use your own body weight.
Still have to do energy, but like, yeah, okay. I like this idea. So now we're going into the concept, right? Okay, so we have this slope. It's 1 meter high. So you have to build this ramp in your house, and you have your cart, right? Has your mass in it, and then you push it up the hill every hour. So you're sitting there writing, like sweating, because you just pushed this up an hour before. How big is this slope?
No, you don't push a mass. You go to the first floor, you sit on a chair, and then the chair, you use your own weight.
Oh, that's a cool idea.
You guys do that every minute.
Yeah, so you could do that. People are about 60 kilograms. I like that. So you guys are doing a really cool thing, right? You're going from strategy. We could talk about this like kind of independent. This is kind of a depiction of a solution, but now you're thinking of concepts, which are physical embodiments of this idea. That's great. Yeah.
If you were saying that it's 1 kilogram will get you 1 second, wouldn't 60 kilograms get you a minute, not an hour?
Oh yeah, you're right. Yeah. Oh man. So yeah, 60 kilograms would get you an hour or a minute. Well, that's exhausting. Yeah, it's giving you a sense though of like how wimpy we are as people putting out power. 10 watts doesn't sound like much, but I always think it's a little funny when people are like, oh, we can just like strap something to a person and charge their cell phone as they walk. You'd feel that. Even a couple watts, you would definitely feel it. It would tire you out if you're walking on flat ground. All right, so this is one idea. What's another one? So the Peltier effect. How would we analyze that? I don't know. They're really low efficiency. I know that. And you need a really high delta T. But one thing I want to touch on is a Pew chart. And we talked about this really quickly the other day, but this is a method that can help you make decisions between ideas on a number of metrics that you can compare them against. So let's say we have all these solutions. So we have, what was the first one? You have the kids. So we have kids, solar, weight. How do you spell Peltier? Okay. Glow stick. Bacteria. And you guys can do, you'd have to do a little background research to do these calculations for these other things, but you could do it. You can look up like how many lumens a glow stick gives out per volume or something. Okay, so what are some categories of comparison that we might use to evaluate these against each other? Cost is one, sure. What else? Recharge time, I like that. I'm sorry? Sure. You could do efficiency, sure. Perception, yeah. Yeah, you guys are getting the idea. So what you can do is then assign, like, the simplest way to do it is to do like 1, 0, -1, right? Or you could maybe benchmark a system, say solar, because you know those exist. Say this is all 1, right? And you could say kids, well, yeah, they may be cheaper, right? So maybe they're also 1. Recharge time stinks. Reliability, terrible. Efficiency, no, awful. Perception, slave labor, right? But, the weight, okay, the weight might be, or sorry, no, you don't do, yeah, you do zeros. Yeah, so do zeros. Yep. So do zeros. Yeah, so like weight, okay, maybe it is cheaper than solar. Recharge time, no, that stinks. You got to run up and down stairs. Reliability, yeah, it might be as good as solar. It's probably better than solar actually, because you always know that weight's there. You don't have, cloudy weight days. Efficiency, no, that's terrible. Perception, yeah. So you can add these up, and you can see this would be less than 0, that would be less than 0, and it gives you a benchmarking between the ideas, right? So this is a nice way, and this would be total over here. So you can add them up on the rows, but it gives you a nice way to compare a bunch of categories of an idea and evaluate them relative to each other. You also may want to put multipliers on these. So you could do like ×2 because cost is really, really important, or perception, like, you know, ×5 because if a person looks ridiculous, they won't buy it, right? So there's different ways you can manipulate this to weight different factors and stuff. But that's a tool I definitely want you to use. All right, so as we're wrapping up, there's actually solutions to some of these ideas that we were coming up with, some of these strategies. So you guys familiar with the socket? This is a soccer ball that has some sort of weight that can move around inside it that kids go out and play soccer with. It charges, and then you come home and plug a light into it. What do you think of this?
It's probably not very good for soccer.
Why? Because how would your energy of the system scale in this case? Right? You have to think about the kinetic energy somehow being absorbed by the ball. So your kinetic energy is equal to 1/2 mv squared, right? You would want a higher mass ball that you're accelerating and decelerating to get more energy. But what's that mean for soccer? It stinks, right? Also, it could hurt somebody if it's really heavy. Also, just from a perspective, like how many people are on a soccer team? Right? You have at least 11 on the field, right? And then you have 11 other people. So you have 22 people on the field. How many soccer balls do you use in a game? Oh, must be nice for that one kid who gets to go home and light their house. Yeah, it's not scalable at all. But this has gotten a lot of money. It's really popular because the idea is really compelling. Like, oh, kids are boundless energy. You know, they can charge balls and go home and light their house. It's nuts. Okay, look, this solution actually, it's kind of dark, but this thing actually exists. Look, it's a big bag of something that you're hanging from a light, and it goes down like a cuckoo clock. How much light do you think this thing can put out? Not much. The whole picture's dark, right? Not 10 watts, I guarantee you. Fraction of a watt. You know? And I suspect somebody would probably use this and be like, this thing's not very bright. Let's put more weight on it. You know? It might break it. But like you guys, like this is a real thing. You can go buy these things, but you guys can do this calculation super quick and be like, that's not going to light a house. It may be a night light or something that goes off by the time you have to get up and go to the bathroom because it's already fallen to the floor. But you know, you guys have the ability to do that. And so solar, you know, we did the quick calculation. Solar seems like it's pretty compelling, and you can see in the market there's a lot of solar solutions. And this is cool. So, you know, this thing over here, the D-Light, you can see we're pretty, that's about, you know, that thing's about this tall. And so this thing is about our 0.15 square meters. Like it's around the right size. And you can throw this on your roof and you can light a light for a number of hours. Right? We are pretty in the ballpark of how these things actually work. This one's a smaller panel, and this gives off less light comparatively. This product kind of drives me nuts because it just looks like nice and fun because it looks like a sunflower. But look how small the little solar panel is, and look at the form factor. Right? So you either put the light down on the table to charge a panel, or you put the light facing right up so it's like in your eyes. Like, how do you hang it? Actually, no, their logo says how you hang it. And then this would be a bigger lighting solution. But there's reasons, right, why solar has caught on. It is a more scalable and viable solution. Okay, so to wrap up your final couple moments, I want to give you a moment of Zen here. So we're going to watch 2 videos in the last 5 minutes. So let's check out this one.
7 billion of us.
See what you guys think.
Facing some huge problems. Awareness doesn't reduce pollution and grow food. That takes doing. I'm Manoj Bhargava, founder of 5RM. I realize we're making a lot of money.
He has cracked the Forbes billionaire list.
If you have wealth, it's a duty to help those who don't.
you know he's trying to save the world, right? Yeah, well, it's happening over there.
We're going to the invention shop, also known as Stage 2.
It is the most well-funded playhouse for engineers you could possibly have.
Our goal is to deliver products which can directly impact humanity.
If you come up with something cool that's not useful, we don't do it. I have no interest. I don't want to be cool. I actually am never going to be cool. Right now I'm concentrating in 3 areas: water, energy, and health.
The drought has left its mark here.
Some communities could soon run out of water entirely.
China, India, Africa. Now there's a lot of places around the world there's a shortage of water. This is the RAIN project.
We're able to take unusable seawater and turn it into drinking water in a matter of minutes.
This machine can do 1,000 gallons an hour. You create this barge, which has a lot of units on it. Put it a couple miles offshore, pipe the fresh water to land. You get thousands of barges throughout the world. We can address ridiculous amounts of people.
This is our program we call Free Electric.
The idea here is really simple. The person uses a hybrid bicycle. You pedal for an hour, and you have electricity for 24 hours. Millions of people. This will allow them to have unlimited energy, pollution-free. That's everything.
Stage 2 works in medical devices.
We're working on a project called Renew.
It's a product that enhances circulation.
Squeeze blood from the legs back into the core body so it acts almost like an auxiliary heart.
Poor circulation is the basis of a lot of illness. It's not about treating disease, it's about preventing disease.
If you don't think through it, you just put up more hospitals. Now we're also doing that.
So I'll stop it here. This is a film done by National Geographic. Like, this is legit. But I want to call your attention to his water solution feeds water from the ocean to the coast. Good thing people only live on the coast. You know, nobody inland needs water. The bicycle solution, right? You pedal for an hour a day, you get 24 hours of energy, and you get unlimited energy. So to contrast this, I want to show you this video of a person maybe, you know, like, this guy's maybe like a representative developing world user who could ride a bicycle to power an appliance. So let's see what he does. So here's your representative developing world, you know, rural farmer. Oh, happens to be an Olympic medalist.
You ready? It's okay. Handlebar.
Okay. Everyone in positions now. We're getting ready for take. And remember that when Robert loses power, those two will pop up.
There's 750 watts to a horsepower. Just keep that in mind. This guy's a horse. Now, this is an amazing feat of strength. It's unreal.
Great.
Want to lie down?
My legs go.
monster speed.
We do it at the breakfast with the toaster. Nobody can believe how much work it is to toast it. I know it now. It's crazy.
So what do you guys think of that pedaling for an hour in a day and running all your appliances in your house?
But that toaster's pretty inefficient.
Get that many Roberts.
Yeah, the math doesn't work out. You know, this 5-hour energy guy it has great intentions, but the math doesn't work out. Yeah, maybe you need to take 5-hour energy. Okay, as you head out, just couple, there's a few more reading assignments I'll put up. Have your first meetings and all that good stuff.